If it ain't broke, don't fix it. If all you have is hammer, everything looks like a nail. These are two quotes that stand on opposing ends when it comes to new technology that comes into play in orthopedics, in life in general. Um, I've often heard colleagues say, why would I use a new technology because the old thing isn't broke? We don't need to change it. On the other hand, you also have a criticism that as soon as somebody explores a new technology, they use it for every single case. And that's sort of at the other extreme of the coin. When we're talking about 3D printing, the same thing applies. And as we start deploying 3D printing in limb reconstruction, the same is true. We could have, on the one hand, this concept of Maslow's hammer, where everything looks like a nail, and on the other hand, have this concept of why would I even entertain this? Because what I'm doing currently is working so well. My name is Frans Berkholz. I'm an orthopedic limb reconstruction surgeon based at the Institute of Orthopedics and Rheumatology in Stellenbosch, South Africa. And it is my great pleasure to share the next 20 minutes or so with you on my interpretation of 3D printing in limb reconstruction. We know that our limb reconstruction field has always been one with technology, with the advances of technology, but also soundly based in science and in bone regeneration, biology, distraction osteogenesis, biomechanics. All of these things stand at the core of what we do as limb reconstruction surgeons. So it is important when we start looking at new technologies that come into play that they must fit that mold. They must actually fit into our biologically, biomechanically sound way of thinking about reconstructing limbs. So looking at these quotes again, if it ain't broke, don't fix it. And then Colin Powell said, if it ain't broke, don't fix it, is the slogan of the complacent, the arrogant, or the scared. It's an excuse for inaction, a call to non-arms. And maybe at the end of this talk, we will understand a bit more of whether this specific technology is something that's fixing something that ain't broke, or whether it is actually a technology that we can explore and embrace. When I prepared for this talk, I found this specific article very useful. This is from the Journal of the American Academy Global Research and Reviews, and it's a relatively recent review article on 3D printing in orthopedic surgery. So if you want to read something about this topic, this is a good place to start. Now, let's take one step back. What is 3D printing? Now, essentially, if we look at manufacturing things, there are two big ways of creating or manufacturing objects. On the one hand, you can add stuff until you've created your object. That is additive manufacturing. The other one is you take away stuff until you're left with your object, and that is subtractive manufacturing. Now, 3D printing is an example of the first. It's an additive manufacturing concept. Maybe it would be interesting to look at sculpting as an example, where you could take clay and you can add clay to create an object or a sculpture. So that would be additive manufacturing. On the other hand, you could take a block of marble and you can start chiseling away at it, and you are left with, well, in my instance, probably another blob of marble. But if you're a good sculptor, you can be left with a horse or a whatever. So in a way, or in a practical sense, those are the two ways of manufacturing things. So 3D printing, additive manufacturing, the beauty of that is that it doesn't waste as much material. It is relatively rapid. It is also something that can be done in a very bespoke, very planned way, but we'll get into that. Types of 3D printing, essentially, again, two big groups. On the one hand, you have the extrusion method, where you have something like a nozzle, almost like a toothpaste tube, that would then extrude things in layers or substrate in layers, and that would harden, and that would eventually create your object. So typically that would be molten plastic that would be extruded with a hot nozzle, layer by layer by layer, eventually adding up to creating this object. The other way would be where a substrate like a powder or a fluid is subjected to a specific form of energy. It can be light, it can be laser, it can be electron beams, that would then sinter or melt or fuse those substrate molecules together to also create a object that would rise essentially from the substrate. So two very interesting ways of using 3D printing, or two different ways of 3D printing objects. But in principle, the underlying principle is the same. It's a layered approach of creating an object using additive manufacturing. And that can be done in different materials. It can be plastic, it can be nylon, it can be titanium, a variety of materials that can come into play. So the process to go from concept to print is actually stepwise. And the first one, or the first step, is actually to create a digital image. And that digital image is essentially created either by creating something in a design program, like a CAD program, where I design something and I create a digital image of this, or I could take a patient's CT scan or MRI scan, and I could create a digital image, a three-dimensional image of the anatomy. The next step then is to refine that digital image. So in our terms and medical terms, we would then take the CT scan data and we would take away everything that is not of interest to us. So everything that's not bone, that's not going to be printed, we need to remove from the image. And that's what refining means in this context. Then we create what is called an STL file, which is essentially a file format for 3D printing. And that then goes, it's standard triangle language or something of that nature. And then that gets translated into a code that the printer can read. So basically a little recipe for the printer as to how to go about printing this object. That gets pushed to the printer, and hey presto, you've got your new object, whether it be a titanium implant or whether it is a plastic model of a patient's foot. Right, benefits, we've touched on this. Some of the main benefits of 3D printing is that it is custom. You can really make what you specifically want for this instance very accurately, very specifically on a once-off basis with this technology. The second thing is the detail. You can actually create something that you would not necessarily be able to create in a standard manufacturing process. So for example, if I've got very intricate internal detail that I want to create, it is sometimes extremely difficult to do that with, well, it's almost impossible to do that with milling, for example, because your bits, your milling machine can actually not get inside the object to actually cut out little bits and pieces. So you would have to create your object in pieces and then assemble it at the end. With 3D printing, you could actually print a whole gearbox inside too, and it would actually work because the resolution is of such a nature that you can do that. So that is sort of the second benefit of 3D printing. And one of the third benefit is really cost. And, that cost is quantified in terms of dollars, money, or in terms of time. And it is actually quite a lot cheaper to create a custom implant on a once-off basis using 3D printing technology than it is to create molds or a milling machine to actually make it. So in that sense, you're saving money, but also time. Now, time is relative, as we all know, and Einstein has told us, in the sense that it takes quite long to actually physically print the model. It can take 14 hours or 16 hours to physically print the model. But where you save time is actually in the creation of the whole process, where from start to finish, your time spent to create a new custom print is not as much as it would have been if you had to build molds or if you had to program a CNC machine, for example. So that is where the cost benefit comes in. If we take a step back and we look at potential applications for 3D printing technology in orthopedics in general, they are divided into a number of things. The first one which I find very interesting, is anatomic models. And these are basically where we create a 3D printed anatomic model of a patient's specific anatomy for a specific purpose. And generally, there are two reasons why we do this. The first one is for education purposes or for information purposes, where we create a model that basically represents the patient's anatomy so that we can understand it better. And the second one is for surgical rehearsal, where we basically create a model so that we can operate on that model, plan a surgery in detail, and execute that plan in a safe environment. In other words, there's a low risk environment. Once we've demonstrated that we can do that surgery in this way accurately and safely, we can then go to the next step and do it on the patient themselves. So anatomic models created for two reasons: educational purposes or information purposes, something that's also called haptic maps, where we use our fingers and our touch to understand the anatomy better. And then secondly, surgical rehearsal, where we deploy that intraoperatively. Prosthetics and orthotics, really a field that's exploding in 3D printing, where 3D printed fingers and upper limb prosthetics are really becoming very commonplace, and people are building their own little prostheses for different reasons. Difficult to control, difficult to regulate, but that's definitely exploding. On the other hand, orthotics, splints, 3D printed splints, custom casts that you can swim with, things like this, but also custom insoles. So 3D printed custom insoles for foot and ankle purposes are really becoming almost the gold standard in terms of orthotics. If we look at orthopedic implants, we've got the non-custom implants. So these are implants that are created for our inventory. So think of acetabular cups as an example, and you might use 3D printing to create a very specific surface texture that you cannot create in another way for the purpose of bony ingrowth. But it's not an implant that is made custom per patient. It is an implant that's made as part of a inventory, and the 3D printing technology is just used to manufacture a very accurate scaffold, if you will, or a very accurate structure on your implant. So some of the golf clubs use this technology to manufacture them more accurately. Right, then patient-specific instrumentation, really, I think the one that's being pushed down our throat the most is this one, where from a marketing perspective, the companies are really pushing this very hard, and where we are creating 3D printed, 3D planning and then 3D printed cutting blocks and jigs and guides to actually execute a surgery very accurately. Now, interestingly, although this is the one that's the pushed hardest from a market perspective, it is the one that doesn't seem to have the most proof in data, in science, in papers. So it doesn't look like, actually, from our research data, that this actually translates into a patient benefit. Now, it might just be that the studies are underpowered, but probably something to just bear in mind, that this is not necessarily advantageous over the classic way of doing this. Now, of course, once we get into very complex three-dimensional deformities in the limb reconstruction sphere, it might become interesting to actually create specific cutting blocks, specific jigs to actually correct these. I'm thinking Blount's deformities, I'm thinking proximal femoral derotation osteotomies, and so forth. So that could be a very interesting application for this technology. I think a place where we can definitely see a massive explosion is patient-specific custom implants, where we're using patient-specific anatomy to create an implant for that specific patient in that specific context. And that really is a powerful technique, and I'll show you some examples of that. Bioprinting is where we are using 3D printing technology to print cells, scaffolds, tissues, and eventually replacing organs or pieces of organs with bioprinted spare parts, if you will. Interesting in our field will be if we can start printing bone and cartilage. And there's definitely a lot of research in those avenues. One of the challenges is how to keep the cells alive while we're printing with all the shear forces that get exerted during the printing process, for example. But a lot of problems that need to be solved before this can be implemented, but really an interesting space to watch. 4D printing, interesting concept where you 3D print your structure and then you change the environmental parameters like temperature, and that means that the structure becomes soft. You can put it into a space, and then in that local temperature and surroundings, it actually reforms back into the 3D printed scaffold or 3D printed shape. So a very interesting concept of how to create something and then deform it to implant it, and then it sort of goes back to its original shape. And that's what's known as 4D printing. All right, enough of the theory. Let's get into some practical examples. Two use cases where I think 3D printing currently in 2022 are really valuable in limb reconstruction surgery. The one is the creation of anatomic models, especially haptic maps and surgical rehearsal. And the other one is custom implants. And the ones that I use are custom created tailor body implant and titanium truss cages. And I'll show you some examples. A haptic map is really simply just a three-dimensional anatomical model that represents the patient's anatomy so that I can understand that anatomy better by touching it, by walking around it, by really getting to grips with what I'm looking at. Of course, an experienced surgeon can do that off x-rays. They can do that off a 3D virtual image like this one you see in front of you. But for some of us mere mortals, we actually need something a little bit more tangible. And this is what my desk looked like today, incidentally. This is an example of a haptic map of an adult patient with a clubfoot deformity. And you can see as we start zooming in, you can start appreciating certain aspects of the anatomy. Look at that severely plantar flexed first ray. Look at the relationship between the talar head and the navicular. Look at the position of the calcaneus and the cuboid. Look at the subtalar joint. And once we come around the other side, you will see the ankle joint end on. And suddenly you can start understanding the three-dimensional shape of the specific deformity. And you can maybe start thinking of how you would want to address this. Incidentally, the other material you see on the print is just support material that's used when you laying down your layers. Of course, you can't do a layer in the air because it will just drop down onto the bed of the printer. So you have to have a support structure underneath. And in this instance, we printed that in a water-soluble plastic so that I could apply a frame as it is now, and then I can dip it in water and this soluble plastic part would disappear. Surgical rehearsal. Here's an example of a severe cavus foot in a young individual, which I wanted to do a mitre frame for. I'm not very good at planning them so that they don't abut. So I then did a 3D print. And before I took the patient into the OR, I actually operated his foot, his anatomy, with a mitre frame, making sure that my frame actually could do what it needed to do. And then I went and deployed that plan intraoperatively to try and solve this patient's problem. So we can see in this case the osteotomy, we can see the frame that's applied, and then the process of gradual correction of the deformity, and eventually leading to a talar navicular fusion and a plantigrade foot. It's not a great foot, still has a high calcaneal pitch. Mary's angle is sort of restored. Ankle is not very happy, but the patient is quite happy. He's pain-free, he's walking, he's enjoying his life. I don't think we've changed the outcome of this case with 3D printing, but we've certainly changed the process. And we certainly changed the experience in the operating room by knowing what we're getting ourselves in for. And I think that's the benefit of surgical rehearsal. Think of it in terms of pilots doing simulator training prior to being in the real cockpit. So you want to take your risks in a sort of a low risk environment rather than doing it where there's real consequences on real patients. Right, the Other application of 3D printing is by creation of custom implants. Here's a classic example of an avascular necrosis of the talus that was then causing pain. We went ahead and scanned the patient's opposite talus, flipped the image around, modified it slightly by dropping the vertical height by 5% so that it could fit in, and then 3D printed a talus that was in titanium with an oxide coating, and we could then implant that through an anterior approach after removal of the existing talus. And if that doesn't excite you, I don't know what will. As an orthopedic surgeon, that should be extremely exciting to you. That's the approach we use so that we can always come back and revise that if we needed to. But talus pops in nicely. It sits there snugly into its little bed. That hole is for a little joystick that we screw into the talus just to help lever it into place. And that's it after implantation. From there, salvage options would be to pop a replacement at the top or to add pegs and trabecular metal to the bottom so that you can do a subtalar fusion. But at this stage, patient is happy, pain-free, moving, foot and ankle scores have improved greatly. A second example of custom implants is the creation of titanium truss cages, which are used to reconstruct large bone defects or complex bone defects. And really what we're creating is a titanium Eiffel Tower, for lack of a better term, that can withstand the forces quite accurately. It's roughened so that it adds the ability for bone to grow onto and into that structure. The structure will get filled with bone graft prior to implantation. But there's the example. So really bad periarticular bone loss, modeling that defect, 3D printing that specific truss cage for the specific patient that gets filled with bone graft from a reaming and then gets implanted into the defect and secured in place using, in this instance, a hindfoot nail from the bottom. In a very elegant way to eliminate a very large bone defect, which would otherwise need prolonged segmental bone transport procedures. This is one of the follow-up visits, of course, not consolidating yet, but we're waiting with bated breath to see consolidation in this instance. Of course, the truss cage is extremely strong, can withstand up to 2 tons of force. So the question is, if it doesn't consolidate or incorporate, whether that would be such a bad thing. And, you know, the data is being collected at the moment, so we'll know these answers soon enough. Here's another example that's currently in hospital, currently occupying my mind. It's a previous gunshot injury, multiple operations, ended with that horrible piece of little fluffy bone there in the middle, a regenerate that didn't really form, and that was grafted with all kinds of artificial bone substitutes. So really soft and iffy, cloudy, rubbishy little piece of bone there, which we opted to excise and then convert this whole construct into a lengthening nail. So we have the titanium cage in there that is fixed to the bone with little extension plates on either side to hold it together so that we can distract through that area through the osteotomy at the top, because of course our lengthening nail is attached there and there, and if our cage was not secured, it would actually just dislocate. So this case, I will hopefully be able to show you the outcome of next year at the whole meeting, but an interesting concept of employing different limb reconstruction techniques to try and solve a very complex problem. So is this the solution to limb reconstruction surgery? We will need to find out where this technology fits into our armamentarium as limb reconstruction surgeons, whether it's just a gimmick or whether it's actually a real-time solution that will change our patients' lives is yet to be seen. And it's up to us to actually do that and explore that and see where this technology fits into our field of orthopedics. With that, I thank you.